Welcome to Tales from the Periodic Table. I'm your host, Ron Hipschman, and today we're going to talk about the element neodymium. I have a sample of neodymium in this glass vial right here. Let me show it to you really quickly. It's kind of a silvery metal, as you can see, but it's kind of hard to see from this sample. So let me bring up the slideshow again. I have a closer scan of it for you. Here you can see it a little bit closer. Maybe we'll even look at that even a little bit closer than that. It's shiny and silvery here because it's kept from oxidizing in the air. This sample would turn black in a few minutes if exposed to oxygen. Here we see the beautiful periodic table produced by Theodore Gray. As I've mentioned in previous episodes, Theo has written one of my favorite books called The Elements, which I encourage you to pick up. Check out his fantastic website, periodictable.com. Neodymium is the 60th element in the periodic table. Its atomic number is 60 because that's how many protons are in its nucleus, and that is what distinguishes it as a unique element. In 1751, Axel Cronstedt discovered a mineral from a mine in Basna, Sweden. 30 years later, 15-year-old Wilhelm Hisinger, whose family owned that mine, sent some to Carl Scheele to analyze, but Scheele failed to find any new elements. Another 22 years pass, and in 1803, Berzelius and Hisinger examined it themselves and isolated a new oxide that they called Syria, after the newly discovered asteroid Ceres. Move forward another 36 years, and Swedish surgeon and chemist Carl Gustav Mosander, who lived in Berzelius's house, by the way, separated out two oxides from Syria, which he called lanthana, which was actually lanthanum oxide, and didymium. Turns out that didymium is not a pure element, but rather a mixture of rare earth elements. It was not until 1885 that Karl Auer von Welsbach separated didymium into our previous element in this series, praseodymium, and this episode's element, neodymium. Remember didymium. We're going to encounter that later. A pure sample of neodymium metal itself was first produced in 1925 by Howard Kremers. Sources of neodymium are the minerals monazite and bastnasite. Monazite is a phosphate with lanthanum, cerium, and neodymium as substituting elements. It's usually found in the form of a sand with other constituents. India, Madagascar, and South Africa have large deposits of monazite sands. As I mentioned in the previous slide, another source of neodymium is bastnasite, which is a carbonate fluoride with yttrium and other rare earths as substituting elements. These minerals are mined for many of the rare earth elements. In monazite and bastnasite, neodymium can be found in percentages up to 15 and 20% respectively. The name neodymium is derived from the Greek words neos, meaning new, and didymos, meaning twin, hence new twin. Combined, we get neodymium. Remember didymium? The dymium part comes from didymium. That was separated by Mosander into praseodymium and neodymium. Neodymium belongs to a row of elements known as the rare earth metals, or lanthanides, since lanthanum was the first element in this periodic row. Neodymium is the fourth element of this series. Technically, both scandium and yttrium also are included in this group, since they're both members of the same periodic table column. Both the lanthanide row and the actinide row below it actually fit in the two spaces after barium and radium. But if we display the table in this fashion, it becomes too long and unwieldy. Rare earth production, including neodymium, has grown exponentially since the 1950s, doubling about every 15 years. Early on, production was small and scattered. The U.S. got into the game around 1965. China started producing 20 years later in 1985 and has since dominated production. Let's expand and magnify production since 1994. Notice that the U.S., the green areas, and Russia, the smaller magenta areas, turned down production and leave the game in 2005, unable to compete with China. However, in 2010, China drastically cuts exports, coaxing the U.S., Myanmar, and Australia to start or restart production. China is still the 800-pound gorilla, but now there are other sources as well. The only rare earth mining and processing facility in the United States is the Mountain Pass Mine, 53 miles southwest of Las Vegas. The mine supplies almost 15% of the world's rare earth production. While this mine specializes in praseodymium and neodymium, they also extract lanthanum and cerium, as well as a few other rare earth elements. As with most elements, the price of neodymium varies widely with purity and the quantity you buy. 99% pure neodymium goes for about $58 per kilogram. Fairly cheap given its apparent rarity. The price of neodymium has remained pretty stable for many years. That spike occurred when China restricted its exports. Note that this is the pricing of neodymium oxide, but it tracks pretty well along with the pure metal. The element neodymium is fairly uncommon in the universe, coming in as the 34th most abundant element in the universe by mass at about 1/1,000,000%. At 48th, neodymium is pretty rare in the Sun, at 3 parts per billion. It's the 47th most abundant element in meteorites, at 500 parts per billion, and surprisingly common compared to everywhere else. In the crust of the Earth, it's the 28th most common element, at 33 parts per million, almost 4 times as common as lead. Neodymium is the 68th most abundant element in the oceans, virtually non-existent at 2.8 parts per trillion. And lastly, and not surprisingly, there is no neodymium in us. This complicated version of the periodic table shows the evolution of the elements through the history of the universe. Here, you see each element square with a tiny chart of its own showing that element's growth over the age of the universe by various processes. Neodymium is here. I understand this looks complicated, but let's look at just neodymium a little closer. The horizontal axis of this square represents time from the Big Bang to now. The vertical axis shows the proportion of neodymium created by various processes. The vast majority of neodymium present today is believed to be produced by dying low-mass stars, the magenta area. A smaller amount is produced in supernovae, the yellow area, and a very small portion, that green sliver on the top, is produced in neutron star mergers. Each element has many different forms. For each specific element, the number of protons in the nucleus is the same, 60 protons for neodymium, but there can be different numbers of neutrons in the nucleus. All these different forms are called isotopes. They're chemically identical to each other, but with slightly different weights. The number you see next to the chemical symbol is the total number of protons and neutrons in the nucleus. There are 38 known isotopes of neodymium, and of these 38, there are 5 stable non-radioactive isotopes. These 5 stable isotopes are found in different proportions in nature, from about 6% to almost 27%. The astute among you will probably notice that these 5 isotopes do not add up to 100% of the neodymium in the universe, only 70.6%. Well, where's the missing 29.4% of naturally occurring neodymium? There are actually 2 very long-lived radioactive isotopes that make up the rest, neodymium-144 and neodymium-150. These 2 make up the remaining 29.4%. More on this in the next slide. By the way, the word isotope comes from the Greek isos, meaning same or equal, and topos, meaning place, since all these various forms of neodymium occupy the same place in the periodic table. Of the radioactive isotopes of neodymium, these are the longest lived, the ones with half-lives over 1 hour. More on half-life in the next slide. The longest neodymium half-life is neodymium-150 with a half-life of 6.7 quintillion years. That's about 485 million times the age of the universe. The half-life of neodymium-144 is only 2.3 quadrillion years, less than 1,000th neodymium-150's, but still 166,000 times the age of the universe. With such long half-lives, you can see why they still occur in nature. They haven't had time to decay away yet. What's a half-life? This graph shows an exponential decreasing curve. As an example, let's say we start with 1,024 atoms of any isotope from the previous slide. You'll see why I chose 1,024 atoms. Hint, it's a power of 2, and we'll be doing a lot of divisions by 2. If you wait 1 half-life, half of your isotope will decay, and you'll have 512 atoms left. If you wait 1 more half-life, half of that half decays, leaving you with 1/4 of the original 1,024, or 256 atoms. Another half-life, half again is MIDI, or 128 atoms, and so on. Just keep dividing by 2 every half-life. After 10 half-lives, you'll have about 1/1000th of your original amount. By the way, notice there's 1 remaining atom after 10 half-lives. If you waited 1 more half-life, your remaining atom would have a 50-50 chance of decaying in that time. Neodymium has a medium density at 7 grams per cubic centimeter. As a reminder, water has a density of 1 gram per cubic centimeter. I've put up more densities for you here. You can see that neodymium is a bit less dense than iron at 7.89 grams per cubic centimeter. Here's a graph of the elements from highest density to lowest density. When I do this talk with an actual audience, I have a set of blocks so you can lift and feel density for yourself, but we'll have to wait to do this until we're back face to face. My set of blocks have a wide range of densities, with the densest at tungsten, to lead, to copper, to iron, to titanium, to aluminum, to magnesium. I also have plastic and wood blocks, but those are not technically elements. Again, neodymium's density is 7.01 grams per cubic centimeter, the magenta circle, between titanium and iron. Neodymium has a fairly low melting point at 1,021 degrees Celsius, or about 1,869 degrees Fahrenheit. It boils at a fairly high 3,100 degrees Celsius, or 5,612 degrees Fahrenheit. That's a full 2,079 degrees Celsius above its melting point. Quite a difference. If we compare the size of the neodymium atom to that of hydrogen, we'd see something like this. The neodymium atom is about 4 times the size of hydrogen, Those two outer electrons are held fairly loosely, making for a larger atom. By the way, a picometer is a trillionth of a meter. Atoms are small. Here are atom sizes sorted from largest, cesium, on the left, to smallest, helium, on the right. Neodymium has the 19th largest size atom of all the elements. All the rare earths are fairly large. Neodymium is a very soft element, coming in at only 1.23 on Mohs scale of hardness. You could easily scratch neodymium with your fingernail and cut it with a knife. Here's a chart of element hardness from the hardest, boron, on the left, to the softest, cesium, on the right. Neodymium is the 9th softest element, just a bit harder than the softest element, cesium. It's the softest of all the rare earths. Neodymium has the 34th highest rate of thermal expansion, about 10 parts per million per degree Celsius. This means that if you had a 1 meter long bar of neodymium and you heated it by 1 degree Celsius, it would get longer by only 10 millionths of a meter, or about 1 hair width. A pretty low expansion rate. Aluminum expands 2.4 times as much. Here's the periodic table of the spectra. Neodymium has a very complicated set of emission lines across the spectrum. It's generally regarded as having one of the most complex spectra of the elements. Let's take a look at a few applications of this rare earth element. When you hear neodymium, most people think of those amazingly strong magnets. They come in all shapes and sizes, strengths, and magnetic field arrangements. Although these are regularly called neodymium magnets, they're really mostly iron with a bit of boron in there too. About 82% iron, almost 12% neodymium, and almost 6% boron. These magnets are strong enough to clamp jewelry to clothing, or an earring right through the lobe of your ear if you're afraid of getting a piercing. You'll find a pair of neodymium magnets in the hard drive inside your computer. Let me remove the top magnet. The magnets surround a coil of wire which acts as a motor, moving the tiny read-write heads across the disk platters. If you have an old hard drive like I did, take it apart and admire all that technology inside. Just make sure you never want to use it ever again. Here's one with its disk spinning and heads moving, just to give you the idea of what it looks like when it's working. This is a micro drive. The platter on this drive is only 1 inch across. It may not store much, but it fits in places where no drive normally fits, like in your camera. Your earbuds probably contain a neodymium magnet too. These tiny speakers require a strong magnetic field to produce full-bodied music with such tiny speaker cones. Strong magnets also make tiny motors with high torque possible, like this toy motor, or very high torque motors like this much larger General Motors EV car motor. You're supposed to attach this neodymium magnet to the side of your transmission, where it's supposed to attract bits of iron ground off your gears. It's supposed to hold and keep the wayward particles from further damaging the transmission mechanism. Does it actually work? I have no idea. I already mentioned that Carl Gustav Mosander thought he discovered an element called didymium. Remember that didymium turned out to be a combination of both praseodymium and neodymium. Well, Sir William Crookes discovered that when these two elements were added to glass, they tinted the clear glass with a pinkish color. This glass is called didymium glass, and it has some unique light-blocking capabilities. Here's the absorption curve of didymium glass. I know some of you may not be familiar with the color of light associated with those wavelengths along the x-axis. Let me just put up the corresponding colors behind the graph so you see them with their wavelengths. Ultraviolet is to the left of visible light, and infrared is to the right. The didymium glass blocks yellow light quite well. Specifically, it blocks the light given off by excited sodium atoms almost completely. Notice that the percent of yellow light transmitted by this filter is virtually 0%. Although you can only see it partially in this graph, the light also blocks infrared light quite effectively. Why is that important and useful? When glassblowers are doing their work, the glass working flame hits the heated glass, which contains sodium. The sodium glows in a blindingly bright yellow light. It's hard for glassblowers to see what they're doing. If the glassblowers wear didymium glasses, the yellow light is blocked and the melted glass is much easier to see and work. In addition, blocking infrared also protects the glassblower's eyes. Because of the strange color absorption curve of didymium glass, you get the odd effect that it looks different under different illumination. Here, we see the same 2-inch square of didymium glass under incandescent light on the left and fluorescent light on the right. This is due to the differences in the spectrum of light passing through the filters. Here's the spectrum of incandescent light on the left and fluorescent light on the right. The light passing through the filters combined with the absorption spectrum of the didymium glass seen a couple slides ago creates this effect. Let's look at another example. Here is the same light bulb with a didymium glass envelope under fluorescent light on the left and incandescent light on the right. A stunning difference. This is the same piece of glass. Notice the shape of the breaks and cracks. We'll see this effect yet again in a few slides. I don't know if this is legit or not, but here's a light bulb for reptilian terrariums that claims to be full spectrum, which is supposedly better for your cold-blooded pet. They do this with didymium glass, though the box says neodymium. Since didymium glass blocks certain colors of light, I don't understand why this is considered full spectrum. A normal incandescent lamp has a fuller spectrum. I think they need more scientists in their marketing department. These fellows are the Moser brothers, Carl, Richard, Leo, and Gustav, whose father, Ludwig Moser, founded the famous Moser Glassworks, which is still producing some of the most beautiful glass in the world. One of the brothers, Leo, took over the glassworks and made many innovations, one of which was to introduce the use of rare earth oxides as glass colorants. He investigated the use of neodymium in glass coloration in the late 1920s. Here's one of Moser Glassworks' beautiful pieces. This one is made from didymium glass. Here is a Moser didymium goblet under fluorescent and incandescent light. Because of this color change, this type of glass is often mistakenly called alexandrite, which is a rare gem that also changes color under different lighting. The alexandrite gem does not change color because of rare earths. Rather, it's because of the light-absorbing qualities of a different element, chromium. Carbon arc lamps use a mixture of rare earth elements to improve the light quality. This type of lighting, especially as used by the motion picture industry for studio lighting and projection, consumed about 25% of the rare earth compounds produced until carbon arc lamps were phased out. The rare earths were placed in the core of the carbon rods and made them burn with a beautiful white balanced light, perfect for film. You may have seen carbon arc light sources used in giant spotlights in the front of store openings or movie premieres. This one's just a sad attempt to sell office supplies. No glamour there. Most carbon arc lamps have been replaced with short arc xenon tubes. These tubes last longer than the carbon rods, and there's no flames to worry about. Another application of making light rather than absorbing light is neodymium's use in lasers. A slight impurity of neodymium is added to a substance called yttrium aluminum garnet, or neodymium YAG for short. To the eye, this colors the normally clear YAG crystal the same pinkish color as didymium glass. And when exposed to a high-intensity flash of light, this crystal glows and can be used as the active component of an infrared laser. The actual laser might look like a boring box, but what it can do is quite useful. That laser can be incorporated into other devices, like this hair removal laser, or the very similar tattoo removal laser. Although several treatments are usually required, tattoos can be removed or lessened with laser treatments. This works because the laser is absorbed by the relatively large tattoo ink particles, which are broken up into smaller particles that can be absorbed by your white blood cells and moved out of your body. This is actually an alexandrite laser that you're seeing here. Remember alexandrite from a couple slides back? But neodymium YAG lasers are also used. This is from the Smarter Everyday YouTube channel, which I always find fascinating and highly recommend. If you thought that neodymium-doped YAG lasers were all desktop affairs, we move to the world's most powerful laser. The Lawrence Livermore National Laboratory hosts the National Ignition Facility, or NIF. This laser is so large the building housing it is bigger than the size of 3 football fields. The giant lasers inside this building are used to experiment with fusion power, explore matter at extreme densities and temperatures, and to help maintain our nuclear stockpile. Here, you see half of the 192 lasers that make up NIF. Note the people near the bottom just to get some scale here. NIF uses 3,072 slabs of neodymium glass to amplify the brightness of their lasers. That's 16 of these for each of the 192 lasers. Here you see a complete laser amplifier, which is energized by the largest flash tubes in the world. The laser starts off as a relatively weak beam and is amplified a quadrillion times. That's 1,000 million times. I'm going to let the NIF narrator describe these neodymium amplifiers in their excellent animation.
As we track 8 of these beams through the facility, you can see the path of the beams highlighted in red. The first amplification occurs in the power amplifier. It has 5 glass slabs that were energized by the powerful flash lamps. Then they travel to the main laser cavity that directs the laser light back and forth 4 times through 11 sets of laser amplifier glass in the main amplifier system. This gives the laser beams another boost of energy. During this time, optical components ensure that the beams maintain their required pulse shape, quality, and spatial uniformity. On the final pass through the optical system, the laser light is allowed to exit.
After reflecting around to get the beams in the right places, the beams finally end up entering the huge target chamber. Here, the infrared beams are converted to ultraviolet and converge on the target. The beams enter the 2 ends of a cylinder known as the hull-rom. The hull-rom is heated by the lasers, giving off X-rays. These X-rays heat and compress a tiny 1 millimeter capsule of hydrogen, bringing it to the pressure and temperature at the center of the sun and to the point of nuclear fusion. Neodymium is big science. Your body does not use any neodymium, and it has no known biological function in humans. Though there's no biological role in humans, it is used by certain types of extremophile bacteria, such as this methylacidophyllum fumariolicum. These were first found in 2007 in hot mud pools surrounding volcanic vents near Naples, Italy. This is a similar volcanic mud pot in Yellowstone National Park. The early lanthanide elements such as lanthanum, cerium, praseodymium, and neodymium are used by the bacteria to break up methane to feed the organism. How amazing that these bacteria evolved to use such elements as an essential part of their metabolism, and in such an extreme environment. As usual, we'll end this talk with Mary Soonlee's elemental haiku about neodymium. Delved from China's mines, mixed with iron and boron, strong magnets, high costs. In the next program in this series, we'll examine the next of the rare earth elements called promethium, the only radioactive rare earth of the lanthanides. I hope you'll join me. I'm your host, Ron Hipschman. Thank you for watching this Tales from the Periodic Table program about neodymium.